Good morning and welcome to the next lecture in Statistics for Data Science, which is still in the field of Bayesian inference, but today is concerned with Bayesian filtering, which, I think it's definitely fairly close to what we've done last time in terms of conjugate Bayesian inference, although I think the wider world not necessarily thinks, when they think of the Kalman filter, immediately of Bayesian inference. That depends a little bit on where they are coming from, but it's kind of Bayesian inference where the Bayesian is not stressed that much. It's more probabilistic modeling. Of those who are not in cognitive neuroscience, who has heard about the Kalman filter before? Okay, in which context?
I done it in my bachelor thesis. So, this was still for nonlinear transformations.
So then you should know some of this material definitely. And you? How do you? A bachelor thesis, okay. And in what subject would that be? So when you do your bachelor thesis, that was in which kind of working group? Mathematics. Okay. But in which, which part of mathematics?
Stochastics, tied together with numerical methods.
Yeah. Good. Yeah. So some neuroimaging people would have heard of that. Yeah. And what was it framed in terms of Bayesian inference then, or was it? Yeah. That also makes sense. Good. So in a way, you can view this whole thing as basically doing So what we're doing today, doing conjugate Bayesian inference, if the parameter varies over time, if you want. So that's the connection to last week. I follow here quite closely this book by Serke, or however you pronounce him, which is a nice small book that focuses exclusively on filtering, smoothing in state space models and their nonlinear extensions, a little bit of parameter estimation also. And it's quite nice because it's very accessible, but still formal enough so that one can actually implement things. And it's also nice because it's just concerned with this, and you can find material on Bayesian filtering, Kalman filter, in Markov models, state space models, in any machine learning textbook or engineering books often also. But then they are usually embedded in a bigger story, and it's not that focused. So this book by Serke is really nice, I think. And a little bit from our own work somehow also went into this. At least that's how I feel. That would be the outline. So first I'm going to introduce the foundations, which is mainly the definition of probabilistic state space models, what they are, and then introduce the idea of Bayesian filtering and its specific case, the Kalman filter, then Bayesian smoothing and the Rauchtung-Striebel smoother, and then show you one example and point to some extension. So when you did your bachelor thesis, was this also with smoothing included? Or?
No.
Right. But the extension is very straightforward. So first, some general remarks on why this is interesting, and somehow more emphasis on applications and the general context than in other sections where I always hope it's self-evident why this is important, but maybe because Bayesian filtering is a little bit more obscure. Here are some remarks. So first of all, you can view it as Bayesian inference in dynamic parameter scenarios. So for example, if you think of last week, if we have a better Bernoulli model or better binomial model where the parameter that governs the emission or the sampling of ones in this binomial model or the Bernoulli model changes over time. then this would be a dynamic parameter. These dynamic parameters in what we're doing today are called states, so they are latent random variables, not directly observable random variables that change over time. Of course, a specific case of changing over time is to not change over time. So in this case, that's then the conjugate inference stuff can be considered a special case. Yeah, that's just a kind of big word to say. So what you actually want to do is to estimate some latent states in some model based on observations. And these you have time-variant systems, and you want to estimate their states based on observations and the inclusion of observation noise. What that really means, we will see once we have it defined. One reason why I went into that in some depth is if you think about dynamic models in physics and the sciences, they are usually framed in terms of differential equations. They can generalize differential equations to stochastic differential equations. And if you, again, discretize stochastic differential equations and consider them your model, that then is subject to some observation noise, and you want to, based on some data, infer on the stochastic differential equations, then you do this by Bayesian filtering. So it's a crucial step when thinking about data analysis for very general models. Stochastic differential equations like being a very general model class, because on the differential equations you can view them as special cases and so on. And then filtering plays an important role. Another name under which you actually find Bayesian filtering is data assimilation. So assimilate. That's you might know that there's a Sonderforschungsbereich data assimilation here at Potsdam University. So data assimilation is Bayesian filtering, as they call it in the atmospheric and oceanographic sciences. So when they say data assimilation, you might think, oh, that can be anything. But what they mean is Kalman Filter, Rauchtung, smoothing. So basically inferring on dynamical models based on data. And that's atmospheric and oceanographic sciences, so things like weather prediction, climate change. And then it also, that's just more for the nerds and neuro people. Bayesian filtering methods are also behind what the current theories about what the brain does. So brain theory, climate change, everything is Bayesian filtering. And not only climate change and the brain, but also artificial intelligence is also Bayesian filtering. It's really like that. So this is why Bayesian filtering is actually important. So if you think about current AI applications that work in this reinforcement scenario, so where you have these nature publications that some AI algorithm can play a computer game. This is usually in the reinforcement scenario, which is in the POMDP scenario, which is in a generalization of the Bayesian filtering scenario. Yeah. So AI, climate change, actually also missile control. So everything that's happening in the world these days is actually rests on Bayesian filtering methods. It's actually like that. So it's an important topic. So just some more application areas: GPS. So your GPS unit, target tracking. So hitting some Iranian generals. You need some Bayesian filtering. Then integrated inertial navigation, which is what the Apollo 11 lunar module did. That was also based on the Kalman filter. You might know that when Neil Armstrong, when they went on the moon in this thing, they got this error message from the computer at one point. So there was error like error 2180 or something they got when they were flying over the moon. And then they didn't know what to do, and essentially they said ignore it. What that was, apparently, as I understood it, was that their Kalman filter that was estimating where they were going was clogged essentially, so that it ran out of working memory, and they still were able to land. So maybe it's not that crucial, but that's where Kalman filter played, or Bayesian filtering played a role during the lunar landing, weather prediction we already mentioned, general fusion problems, computation, quantum new science. I just brought them up again. Brain imaging, POMDPs. Yeah. So Bayesian filtering is behind everything that's going on in the world. Any other things you would like to add from what you have studied? No. Good. So that was kind of the general remarks without pictures, but still making a big case for Bayesian filtering and smoothing. And now let's have a look. Yeah, I mean, I could also have included here, which I didn't include, is you can also see Bayesian filtering closely related to hidden Markov models, which then before neural networks were the main speech recognition method. So also speech recognition based on Bayesian filtering. So everything has to do with Bayesian filtering. So now Bayesian filtering, what's going on? What is the underlying model? So the underlying model is what I call a probabilistic state space model. You might find different names for that. I call it that. And what it is a sequence of conditional distributions where you have random variables that are distributed according to probability distributions. And again, we are in the applied machine learning world where we don't talk much about what this P is. When we later talk about Gaussian state space models, linear Gaussian state space models, the P will be probability density functions. Here it can also be probability mass functions. Then we would be, if it's only probability mass functions, we would immediately be in the hidden Markov scenario. And here we are just a little more general. So we have S0 being distributed according to probability distribution over S0. And then we have ST, S stands for state. That is ST being distributed according to a conditional probability distribution of ST given ST minus 1. So there's kind of a recursive definition of these distributions, and something that we observe, for which I chose X because our observations so far in statistics have always been X, that are distributed conditionally on the states. And this happens for over time points. So T goes from, in this case, 1 to big T. So we, in this case, we think of a finite horizon. You can also generalize that to infinite horizons and so on. But that's how we do it here. T is a discrete time point, so 1, 2, 3, and so on. ST is an n-dimensional random vector that models the system state at a time point T. So yeah, that essentially, so random variable, but more generally a random vector, n dimensions, whatever they model. XT, the observation n-dimensional, that models the system observation at time point T. This transition probability here, or this conditional probability, which I just referred also as a transition probability, embodies the dynamic model. So it describes how the system evolves. So it determines how, based on a current state, ST minus 1, the next state is distributed. And there are ways to translate stochastic differential equations into these kind of discrete transition probabilities. So if you're more interested in that, so how you can get from the differential equation world to this, have a look at what we have published, and you find it also everywhere. So Euler-Maruyama discretization is one crucial thing there. So that's why this is also called the dynamic model. It describes the state dynamics, and then there's the observation model, which describes how observations are happening based on the states. What else do we have? Yeah, that's what I meant. So the P's are not really overly specified here. So can be PMFs, PDFs, or mixtures of both. And as also last time announced, to these small P's I now also refer to as distributions, just because we are in the applied world where if we are too careful in our language, we never get anywhere. one thing to realize about these state space models is that they essentially encode one big joint distribution over all latent state variables. So S0 to T, so I use this colon notation here to, maybe I should have defined that, to refer to S0 to ST. So just to make this explicit. So no, we don't need that actually. What we need is S1, 3. It's weird to write on these PDFs. That's just S1, S2, S3. Yeah, so that's this colon notation. So essentially, if you see something like this, it just means all random variables S0, S1, S2, S3, up to ST, big T, that this joint distribution over all state variables and all observation variables factors in a specific form. Namely, you can write this joint distribution as the product of the marginal distribution over the zeros state variable times the products of the conditional state variable, so st given st minus 1, times the products of the observational random vectors given the state vectors. I think on one of the next slides I will have a little bit more explanation of what's the crucial thing here. But at this point I basically want to stress that a probabilistic state space model defines a joint distribution over all states, random variables or random vectors, and all observation random vectors. From a
maybe we are coming into it later. I don't think, I just want to be sure. So in a sense, we can interpret the state vector as the parameter space we want to, or like the, not parameter, maybe it's the wrong word, but the thing we want to estimate.
Yeah, so I mean, to give a good example, to have a concrete example for that, for example, if it's about target tracking, so if I think the first application of Kalman Filter was in satellite tracking. So you have a satellite that moves in space, and you don't observe where it is exactly, but you observe some signal from it. And then based on what you know about how this satellite is built and where it turns and whatever, you have some idea how it should evolve. And at the same time, you have the observations where you of that where you have some additional noise. And then the state sequence would be the observation of would be the real movement of the satellite. Sorry, the states would be the real movement of the satellite, and you have your observations in your computer, and based on your observations, you then want to infer on the location of the satellite at a given time point.
Can I ask, in this specific example, so I would take, just to have a picture, the XTs from observation would be the signal, for example, and the STs would be the coordinates where
yep.
So we look at the last t coordinates based on the xt signal and try to predict the next.
No, what we do, that's what we will come to, what the problem is. So right now I'm just setting up the model so that you have latent states that evolve over time, you have observations that depend on the states, and what we want to do, it's a little bit explained here, but where you just alluded to, based on what we want to do exactly, what this will come. So currently I'm just saying that there's a joint distribution over latent states and observations, and you can view the state distribution as the prior distribution, and then the distribution over all observations given all states as the likelihood. And in principle, based on this joint distribution, you would now be interested in the distribution over all states given all observations. And if you don't have an online scenario, but you have a full observation set, so from the observations from 1 to t, you may want to try that. However, this is, in terms of Bayesian filtering, not what is actually done. Bayesian filtering things are done recursively and step by step. This slide essentially just tries to link this overall setup of a probabilistic state space model with the general Bayesian inference that we've seen before. But now we make it, I don't know actually how helpful this slide is. It's just, for me it's helpful because it gives the big picture idea and maybe sets you onto not the correct path now to think about Bayesian filtering. But we will see. So that's the general thing one could do. Problem is, so one can also ask later, why do we do it stepwise and why do we not do it like this? And then the answer is because this can be inefficient and it's also often unnecessary if you're in an online scenario. And this is now what is actually done. So one wants in Bayesian filtering, one deals with so-called predicted, filtered, and smooth distributions. And what are those? Because these are the things that are actually created based on the observations when dealing with state space models. Namely, first the predicted distributions, which are the conditional marginal distributions of ST for t going from 2 to 3, given observations xt up to t minus 1. So one question is, what is the distribution over the state random vector given the observations from 1 up to t minus 1. That's called predicted distribution. Here it's mainly about actually getting the terms right. Don't confuse this with this posterior predicted distribution that we discussed last time. That's something different. So this is here just the state variable at small t given x1 to t minus 1. The most important thing in terms of Bayesian filtering, hence the term, are the filtered distributions, which are the conditional marginal distributions of ST for t1 to t given observations xt up to t. So what is the distribution of the state variable, and maybe if we have the distribution of this, maybe also the most likely value of the state given the observations x1 to t. So all observations at time point t. What is the distribution of the state variable? Yeah, so that's the basic question. So you, if you're in an online scenario, you observe observations x1 to small t, and then you ask, what is now my best guess about the value of the state variable? Yeah? And then in an offline scenario, you can also ask, okay, if I have already acquired data up to big T, if I condition the distribution of ST not only on the values up to T, but also on the observations that I obtained later. Yeah? What is the distribution of ST then? Because the assumption is that you have, if you take in the later observations into account, that you have more information, and most likely your estimate will get somewhat better. These distributions, so the marginal conditional distribution of the state ST given the observations from 1 to big T, so all observations, they are called smooth distributions. And we will see that with Bayesian filtering, you evaluate the filtered distributions, and with Bayesian smoothing, you evaluate the smooth distributions. Yeah. So again, with our satellite example, like a satellite, oh love. This would be, you have your observations in your computer up to time 10, and you want to know what are the true locations, or what's your best guess about the true location of the satellite at time 10. This would be, you have, this would be after you actually did some online tracking. You have 100 observations, and you still ask what happened at time point 10, can now better predict it. You can, of course, also in an online scenario go backwards. So if you so to smooth some time back and then use this again as some if you go on. So there one can discriminate things in a more subtle way than this, but for what we are doing, we are happy here with filter distributions. That's the distribution of the state at time t given observations up to time t, and this is the observation of the state given all observations up to big T. Yeah, and predicted and filtered distributions are evaluated during Bayesian filtering, and smooth distributions are evaluated by Bayesian smoothing. Actually, I put Bayesian smoothing and filtering under the title Bayesian filtering, because once you have done the filter, the smoother is straightforward to discuss. So this is maybe a slide that I should have put in a little bit earlier, but now I have it here. Because I'm stressing the conditional independence properties. So this goes back to that the joint distribution over the states and observations is defined in terms of this product. The question is, what does that mean? And what it means is the following. So if you think of a joint distribution of 4 random variables here, S0 to S3, then in terms of conditional probability, you can rewrite this joint distribution by first conditioning on S0 to S2, and then rewrite it in this product. So if you multiply them, you get again the joint distribution. Then you can split up this distribution here and write it as this product, and you can do that once again. Here, you don't need any definitions. This is just a definition of conditional probability. But this means, yeah, so that's the natural decomposition of a joint distribution based on the definition of conditional probability. The crucial thing now about state space models is that you impose some conditional independence properties. What this means is, for example, you say, if you look at here, the conditional distribution of S3 given S0, S1, S2, you say, given S2, the behavior or the distribution of S3 is independent of S0 and S1, yeah? But only given S2. And the same here, for example, S2 naturally depends on S0 and S1, but you can then define that S0 is not supposed to have an influence on S2, but only given S1. So that's the conditional independence. So if you look at the distribution of S2 given S0, there might be still an effect of S1 on it. But if you take S1 into account, so if you condition on S1, then S2 may be independent of S0 if you say so. And that's what's happening in the definition of state space models. So you say, if S2 is given, then S3 is independent of S0 and S1. If S1 is given, then S2 is independent of S0. And if, yeah, here you don't need to specify further independence properties. So this is a little bit, yeah, maybe takes a little bit of time to get used to. If you have a big joint distribution, you can always rewrite it in terms of probability, in terms of conditional probabilities, based on the definition of conditional probability. But then you can, in addition, introduce certain conditional independence properties, and this is what's happening in the definition of a state space model. From these conditional independence properties that you introduce can then follow again other conditional independence properties that you not necessarily define, but then follow from that. So this is like we talked in the beginning about that you can define independence of random variables, and sometimes based on defining certain independence properties, other independence properties then follow. And this is actually what's happening also in the in state-space models. So one in the conditional independence property, or one independence conditional independence property that is very evident from the definition is that the state T is independent of all states that are earlier than T minus 1. That was in the basic definition. But here it's emphasized again that this is a definition and that is not the natural decomposition, and this kind of this definition is called the Markov property, so that the state at time t is only dependent on the state at t minus 1 and not earlier states. But that's, again, that is inherent in the definition of a state space model, but it's emphasized here again. Also inherent in the definition, but not emphasized in the definition, is that the state at time t is also independent of the observations 1 to t minus 1 given as t minus 1. So you should essentially always read these conditional statements as what they exclude, essentially. It's getting a little bit trickier, and this is something that is then also just stated here and not proven. If you look at conditional statements that don't directly involve the conditional independence properties that you define. So, for example, you can ask, what is the probability distribution over t minus 1 given the distributions of the states from t to big T and x t to big T. And then one, based on reformulating this and using only the conditional independence properties that are in the definition of the state space model, one can show that st minus 1 is independent of everything given st. And this, again, introduces the independence of the observations. So with the conditional independence properties, one has to basically always clarify for yourself, if you're in this multi or high dimensional distributions, what is the definition and which other conditional independence properties might follow from that. Yeah? Good. That were basically the foundations, with emphasizing a little bit that conditional independence properties are important. Questions so far? Yeah. Good. Then Bayesian filtering and the Kalman filter. So as previously announced, the Bayesian filtering equations Bayesian filtering aims at giving us the filter distributions, so the distribution over the state given observations, so the distribution over the state at time t, small t, given observations from all observations to this time point. And to do that, it actually also computes the predicted distributions, but the main point is that it computes the filter distributions, so these Bayesian filtering distributions. So how do we get to the prediction? So how do we get to the distribution of st given the observations from 1 to t minus 1? This we get based on what is known as the Chapman-Kolmogorov equation, which essentially states that the distribution of st given x1 to t minus 1 is given as the integral over st minus 1 of the state transition probability, so st given st minus 1, and the earlier distribution st minus 1 given xt minus 1. So if you have this, so if you have the, and the question is, of course, where does this come from? Well, this comes from the filter distribution, because this is exactly the filter distribution at t minus 1. If you have this, you can always compute the new predicted distribution. Yeah. So it's and this will be a common theme here. It's always recursive. So you always assume that you have already something. Now, if you look at this, this is fairly straightforward. So if you do the product here and get rid of this conditioning here, then you have the joint distribution of st and st minus 1. Then you integrate out st minus 1, so you have only st given x1 to t minus 1. Yeah. And then based on the predicted distribution, you can then compute the filter distribution essentially by using Bayes' theorem. So if you have the prior distribution of st given x1 to t minus 1, and the likelihood, if you want, of the observation xt given st, then together you of course have the joint distribution of xt and st given x1 t minus 1. Here, of course, the conditional independence probability plays a role. So in principle here you would also have x1 to t minus 1, but in the definition of the state space model, xt is conditionally independent of st minus 1, everything before that only depends on st. So you can basically form the joint distribution of xt and st given x1 to t minus 1, and then divide by the marginal distribution of xt, which you get by just integrating this over st. So again, the logic is here, you need the filter distribution at t minus 1. From this filter distribution, you can create the predicted distribution at time point t, and from this you can compute the new filter distribution by applying Bayes' theorem. So these are the Bayesian filtering equations in terms of probabilities. And the nice thing to state Kalman filter and these kind of general Bayesian filtering equations is that they of course apply in the same way to hidden Markov models, where these distributions are all discrete. They then look different, and if you study, has anyone studied hidden Markov models? They look a little bit different if you compare them, for example, to the Kalman filter, but the reasoning of why then for example the way to compute the filter distribution based on the hidden Markov model transition and emission probability matrices, why these formulas look a specific way, is because you're basically doing these probabilistic calculus things. We will not look at hidden Markov models in detail, but we will look at linear Gaussian state space models in some detail. Good. This is just to have the same statements over 2 slides. What is then a Bayesian filtering algorithm? So these were the Bayesian filtering equations. Now a Bayesian filtering algorithm. That's an iterative algorithm that computes the filter distributions of a probabilistic state space model using the Bayesian filtering equations. And hence it takes the general form. You need to start somewhere, right? So this was kind of recursive, and at one point you have here t equal to 1, and then you have s0 given x1 to 0, and the question is what that means. Well, for this you take your prior. So this was one component that was defined in the state space model, so you need to define an initial distribution over s0. And then you can evaluate, like previously on the previous slide shown for the with the Chapman-Kolmogorov equation, you can evaluate the predicted distribution. Also for the case that t is 0, because then you just take p0 here for your p as t minus 1 given x1 t minus 1. And that was this then filtering. That's a typo. Nice. I'll do something else. I'll do this again. want to type it. That's of course filtering. Evaluate the filter distributions again on Bayes theorem, like on the thing on the slide before. It's just it's just something different. The filtering equations are not a Bayesian filtering algorithm, but the essence of these two slides is of course completely the same. Now the question is, what is the Kalman filter? And the Kalman filter is now the application of the Bayesian filtering algorithm to a specific state space model. And this specific state space model is defined here. Essentially, this specific state space model is that the transition and the emission probabilities and also the prior distribution over the initial state, they are all Gaussians. And the transitions are and emission functions are linear. So that's the basic point. If you look in the Sarkey book, you can make all these transition probabilities time point specific. So in principle, the parameters of the state space model can also be time varying. I opted here for non-time varying parameters. So we have the following, because it's just easier to look at and also explains quite a lot already. So the initial state is distributed according to a multivariate Gaussian distribution with expectation parameter M0 and variance parameter sigma 0. The states then are distributed according to multivariate Gaussian distributions with expectation parameter given by a matrix product of with a transition matrix A times the previous state and covariance parameter Q. And the observations follow again a multivariate Gaussian where the expectation is given by the matrix product of a matrix, emission matrix B times the state and the covariance matrix R. You can call all of these things differently. I followed mainly the Sarkey notation here with Q and R. You can also give them more meaningful names. For example, call this sigma ST and call this sigma XT, but then again the expressions get a little bit more complex. So this is what I just explained. So S0, n-dimensional Gaussian distributed initial state random vector, expectation parameter M0 and covariance matrix parameter sigma 0. ST, n-dimensional Gaussian distributed state random vector, transition state transition model matrix. So it explains how you compute the expectation parameter of the next random state given a value of the random state. You just multiply that. A state covariance matrix, then the observation model matrix, which often then can project the n-dimensional state vector to a lower dimensional observation vector or maybe a higher observation vector. And the observation covariance matrix, which governs the noise, observation noise. Now, the Kalman filter then is applying the Bayesian filtering algorithm to this kind of model. Before we take a break, let me show you one, because to make this very concrete, to show you a specific instantiation of this model where everything is one-dimensional. Yeah? So the states are one-dimensional and the observations are one-dimensional. So the states are distributed at time point t according to a univariate Gaussian. The A matrix here is just 1. Yeah? So the expectation of the state at time t is just the value of st minus 1, then there's some variance, and then the expectation of the observation is the state at t, and there's some variance. You can also write this, if you like this, so that st is equal to st minus 1 plus some Gaussian error, which is zero-centered, because that's based on linear transformations of Gaussians. And xt is given by st plus normally distributed error. And then the question is how it looks. So here the first st is chosen, and then there's a random addition to it. So it jumps up, and then it goes down, and then it makes these kind of steps, and so on. At one point it goes a little bit higher. And in addition to the state values, there's observation noise, which then yields these XTs. Yeah? So if you want to look more into this, and also for the people who work on the exercise on this, this is the first time, and I'm very proud that I also programmed for this course, and I programmed Python. I'm very proud. So there's some code with this lecture. Yeah, so that's a very simple example of this. So you have this latent state that evolves according to a Gaussian random walk here. As you can see, it walks a little bit around. There's not a very systematic movement because it's just a Gaussian random walk. But this Gaussian random walk is latent. So you have observations of it that don't quite reflect the state, but again have some observation noise. And then after the break, we look what happens in terms of solving the Bayesian filtering equations for this specific model. So we are still here. Any questions right now? No. Yep.
Yes, I mentioned that it's the basis for the reinforcement learning.
Yeah.
In how far?
Well, by that, no, I didn't. So what I meant is artificial intelligence in the reinforcement learning scenario, and by this, what I mean is Markov decision processes and partially observable Markov decision processes, and partially observable Markov decision processes you can view as hidden Markov models with so as state space models with some additional functions that determine, for example, the rewards. So if you set up a Markov decision process, you would usually set up some state transitions and some reward functions that determine how much reward you get in a given state, and then you would ask yourself, how should I decide given a given state so that I make most of my rewards? And if you generalize this to the case that you don't know the state exactly, but you only know observations of the states, then you're in the partially observable Markov decision process scenario, where you then, based on observations, have to infer the states, and that's exactly the filtering here. And you have reward functions that determine your reward based on the state. So you have to do state inference in a dynamic setting, and then based on your state inference, maximize your reward. And that's kind of POMDP agent modeling, if you want. And this is what then people in AI often call reinforcement learning. That's a little bit confusing, because if you think reinforcement learning from the biology or cognitive neuroscience world, you always think of reward prediction error, or it's called Wagner Q-learning. In now more modern computer science, they actually mean POMDP styles. Yeah, it depends a little bit. So if you, in principle, yes, if you look into the papers, so if you think about the DeepMind papers, where they don't tell you what they do, and it's all just advertisement for their company, and nature is happy to help them in the advertisement, because it's really unclear what they do. You can, and I mean, this is what, so this whole combining POMDP models with neural networks for state inference, for example, this was a good source to understand this is the Bertziker's book from the late 90s, Neurodynamic Programming, where this is actually explained. So there he makes the connection between neural networks and POMDP modeling. And this is what the DeepMind people always mean, but then they don't tell you really what they do, because it's their company secret. And it's actually quite annoying. It was really, so the last time that I saw that there's a new paper by DeepMind again, and you don't get the code, you don't get nothing, you just get this message, they have done something awesome. It's like, well, yeah, awesome, that's science. Anyway, So that's the connection there. So POMNI-Ps and filtering in POMNI-Ps.
Thank you.
Good. Then let's have a break and start again 11:15. Okay. Could you close the door, please? Somebody in the back. Thank you. So now we introduce the Kalman filter as the Bayesian filter algorithm for linear Gaussian state space models, which is the definition. Then the question is, of course, how does it look exactly? In engineering textbooks, you find, or sometimes you find in books, many the Kalman filter equations, which, we will now also look at. But of course, the bigger question is what they're supposed to do and why they come out as they come out. And this is basically what we have introduced now. So the Kalman filter equations themselves then look as follows. So the first thing that you can note here is that if all these conditional distributions that define the joint distributions are Gaussian and all the transformations that are involved are linear, then the entire joint distribution is also Gaussian, and also the predicted and the filtered distributions, they are all Gaussian. So you're just dealing with many Gaussian distributions, which means that you're essentially only dealing with the expectation parameters and the covariance parameters of these Gaussian distributions all the time. And you can then evaluate the distributions by applying formulas to the expectation and covariance parameters. Yeah? So the whole problem of inferring the distributions and updating the distributions comes down to evaluating the respective parameters of these distributions. So the first thing then here in terms of the prediction, the predicted distribution, so ST given x1 to t minus 1 is a Gaussian distribution, which has parameters tilde mt and tilde st, where you get these parameters tilde mt by using, and this is the common theme here, by using a parameter of the Gaussian state space model. So R, that was the transition probability matrix, which is assumed to be known, and multiplying it with the expectation parameter at t minus 1. And the variance parameter of the predicted distribution you also get by basically putting together the parameters that you know. So the transition probability matrix, the filtered matrix at t minus 1. The predicted matrix, the filtered matrix, sorry, these are the filtered ones, sorry, don't let me confuse you, we will see them in a second. This is the filtered expectation, this is the filtered covariance, and you apply to this the transition matrix, and you add to it in a square setting, and you add to it the covariance matrix. So before I explain to you where this is coming from, let me finish this with the filtering filter distributions. So this mt and sigma t, which you also see here at the earlier time, mt minus 1 and sigma t minus 1, you get them from using this tilde mt and something called the Kalman gain matrix kt, and something called vt, which is the observation prediction error. And the variance matrix you get from using these predicted variance matrix and subtracting from it this matrix product, where these things are defined as they are here. It gets then maybe a little bit complex. So you have this VT, which is the deviation between the observations. So this is where the observation plays a role, and its prediction. By means of the observation matrix, and And so essentially what this comes down to is that you, what that means intuitively is that you forward your filtered mean forward in time, so you have an idea what the expectation parameter is at t-1. Then you say, okay, the system transfers this into a next expectation parameter tilde mt by multiplying this with a, and then the system based on this forward moved expectation parameter transforms this into an observation by applying b, and then you compare this with the observation so that you get this observation prediction error, and you update your your predicted expectation by this prediction error times the Kalman gain matrix. And the Kalman gain matrix, the thing is, it's a little bit, so it's ideally one would have like a very nice story. And one can if one goes into very simple examples, one can actually make even more of a story for the Kalman gain matrix, for example, how to interpret that. The thing is, these formulas, if you implement this whole thing, they are relatively straightforward to implement. You define parameters like a, q, b, and r. And then on each time point, you need to compute this tilde mt, st, mt, and so on, based on how the formulas are. The question is more, where do the formulas come from? Yeah, and there's a limit to understanding what these formulas do in terms of if these matrices are quite large. Then you lose track of what that really should mean, and so. What I'm trying to say is these formulas just follow from applying these formulas here to the distributions that are defined here. And then they follow directly from the joint. There it is. Sorry, why didn't I make this big here? Sorry. And they follow directly from the joint and conditional Gaussian distribution theorems. So on the next couple of slides, there is the derivation of these formulas for the parameters of the predicted and the filtered distributions. And we will not go over them in all detail. I put as exercises for, as theoretical exercises for the Bayesian filtering session, I put split it up a little bit and put down to go over the proofs, so that we go over the proofs with a little bit more time in the exercise session, the Übung. You find the material here, so for those people who do the Bayesian filtering theoretical exercises, this will be based on this material. So how can one derive these equations here? So this one and this one. Using the Bayesian filtering equations, well, one essentially needs to apply the joint and the conditional Gaussian distribution theorems. You can then say, okay, the proof is really to prove the Gaussian and the Gaussian theorems, but this we will not do, but we will take the Gaussian distribution theorems as given. So what are these Gaussian distribution theorems that I'm thinking of? Well, these are these statements about if you have a marginal joint distribution, a marginal Gaussian distribution and a conditional Gaussian distribution, which depends on its conditional argument in a linear way, then you can immediately write down the parameters of the joint distribution. So this here would be the marginal distribution, a marginal multivariate Gaussian distribution over a random variable x with the expectation parameter μx and variance parameter sigma xx. Here you have a conditional Gaussian distribution, which is given as a distribution over y, which with mean given by a linear affine transformation of x and its own covariance. Based on this, it can be shown, and this is just the theorem, hence the result, that the joint distribution has these parameters, μx, a μx plus b for the respective expectation parameters, and this joint covariance matrix, so sigma xx, the sigma x ata sigma x, and then this sum here of the transformed prior covariance with a square of A plus this. That's the joint Gaussian distribution theorem, which we briefly saw in lecture 3. So that says if you have a marginal Gaussian and you have a conditional Gaussian, the joint distribution of these marginal and conditional random variables is Gaussian, and the parameters you have here. And the parameters you can compute from the parameters of the respective marginal and conditional distributions. From a joint distribution that has a specific form, you can always immediately compute the marginal distribution. Marginal is very simple. So, for example, if you have this joint distribution over x and y, then the marginal of x is has just the expectation parameter mu x and the covariance parameter sigma xx. But you can do more, namely compute the parameters of the conditional distribution of x given y, again based on these parameters of the joint distribution according to these formulas. So you look how far y is away from its expectation, and you scale this with the data variance, if you want, the y variance and the covariance, and use the prime mean in addition to that, and you get this expression for the posterior variance. This means that for multivariate Gaussians, you know how to form joint distributions based on marginal and conditionals, and you know from joint distributions how to condition. So this you know, and based on this knowledge, that of course you can prove, and you can look at proofs in machine learning books or wherever. Usually it's a little bit annoying. So the proofs, when the thing with the proofs is that in the end the proof works with something like Schur complements or something and some matrix identities, and then the question is, where do these matrix identities come from? And then you can go into studying where these matrix identities come from. So for me the limit is a little bit, so I will in my own writing at one point in my little book for brain imaging, I will include a proof of these joint Gaussian theorems, but that's the limit, and most of the time where I stop going into details is actually already at these theorems, because yeah, they then work because certain matrix identities hold. Yeah, they hold because but with these two theorems, one can then prove or derive the filter equations, the Kalman filter equations, by basically using the definition of the linear Gaussian state space model to, for example, derive the prediction equation by first considering the joint distribution, in this case of st minus 1 and st, based on what one has in this recursive fashion. And then, because it's a Gaussian joint distribution, one can use the Gaussian joint theorem to write down the joint distribution. And then one has the joint distribution, and then one can condition, this one can again do using the conditional Gaussian theorem, and for example, based on this joint distribution, then infer what is xt given st given what are the parameters of st, the distribution of st given x1 to t, and essentially it comes down to writing down the filtering equations in general, and then realizing that these are applications of the joint and conditional Gaussian theorems, and then just looking into the parameter equations, and then the equations come out. Yeah. So we will look at this again in the Übung. It is helpful also, why I only felt like I really felt happy with Kalman Filter is if you just learn Kalman Filter this way, you just have these equations, and basically telling you nothing. I mean, you can still implement it, but you, for example, this Kalman gain matrix. I mean, what is this? So if you do the derivation, you see, okay, it's just this manipulation of joint and conditional Gaussian distributions. And if I accept that these theorems on joint and conditional Gaussian distributions hold, then the Kalman filter update equations follow automatically. Yeah? So that's basically what's happening there. And then a little bit rewriting things. So that's how the Kalman filter equations come about. But the important thing is, what is a Kalman filter? Well, it's just the application of the Bayesian filtering equations to a linear state space model. And how do these equations for the Kalman filter come about? What do these equations describe? Well, they describe just the parameters of the filtered and predicted distributions, so the expectation and covariance parameters. How do I compute the parameters in a step-by-step manner? Well, I compute them based on the parameters of the state space model and then using the Kalman filter update equations. So for those who have seen that before, is that roughly what you had in mind? No. Good. Yeah, for those who haven't seen it, for questions about the Kalman filter at this point. If you actually look into the literature, that was not how it was originally derived by Kalman. He looked more into some ordinary least squares optimality for the expectation parameter. Turns out, however, that also Kalman was not the first to deal with that. There is Lauritsen, this statistician in Oxford, I think. He has written quite a lot on some Danish astronomer in the 1900s. I think he's called Thiele, who also developed the Kalman filter in, I don't know, 1850 or something. So it's an old idea. Kalman filter. Any questions? No. Good. Then smoothing. So the big difference between filtering and smoothing, again, is that in filtering we look at the distribution of maybe one brief insert. Of course, if we have the filtered distribution in a Kalman setting, and we think again what we can do with the filter distribution, so we have p as t given x1 to t, then of course we can, for example, use the expected value of this distribution as our best guess on the state, right? So inferring this distribution also means that you can infer the most likely state. And maybe actually before we go into smoothing, I show you that. So this was what we observed, and then I implemented the Kalman filter, yeah, we will work with my code and also with my proofs, so this is also a good chance that you will find any typos or errors in the code. So if something confuses you, ask about it, whoever works on this, because maybe there are things wrong. But this is what I got in terms of the filtered expectations. So you see that it yeah, it's so the green line are the real states. MT is the filtered expectation. So these are the values that you think are most likely given x1 to t. Yeah, and you see that it sometimes looks better and sometimes looks worse. Yeah. But this is what I just wanted to stress, that these filtered distributions, of course, in the end, you also want numbers about where is the missile exactly right now, and then you can make your best guess in terms of the expectation. But now, smoothing. The big difference again between filtering and smoothing, that in filtering you look at the state given observations up to the time point of the state, so st given x to 1 small t. In smoothing, you're interested in st given all observations over a time window that is then usually more than small t. Smoothing then works in a backward recursive fashion, and it works based on the filter distributions. So if you want to do, in addition to filtering, you want to do smoothing, you first have to filter and be able to initialize your algorithm based on S big T given x1 to t, and then move backwards. Although this only features at the, well, it features already here. And to do that, you use the so-called smoothing equation. What's the smoothing equation? Well, it uses the smoothed distribution at t plus 1, as you see here. So as t plus 1 given x1 to t, that's the smoothed distribution at t plus 1. It uses the state transition probability distribution, then it does some Bayesian inference apparently, and averages over that. We see on the next slide why it works. But again, you have kind of a recursive approach, but now that you start from time points that are later in time, so you need the entire data. So this is about the validity of the smoothing equation. So the first thing is to consider, so you want to find st given x1 to big T. What is relatively easy to show is that the joint distribution of st and st plus 1 given x1 to t you can write as follows. So you of course need to assume that you have this smooth distribution. Then you know what's happening in terms of the transition, and then what do I want to show you? I want to show you something. I haven't looked at that for some time. x1 to t. What do I want to do here? Sorry, this I want to show. Sorry, I wonder where this is coming from, but this is what's written here. The first thing is that the joint distribution takes this form. Now the question is, why does it take this form? This is what I just wondered. Well, let's have a look. So with the conditional independence property of probabilistic states model, st is independent of xt plus 1 to t given xt plus 1. So this is something that one in principle should also prove, but I think it was mentioned in these conditional independence properties, and we start there. So the first thing is that st given st plus 1 and x1 to big T is the same as st given st plus 1 and x1 to t, because given st plus 1, so this is going backwards in time, st is independent of observations after small t, which is something where I'm starting from, and which one could essentially also prove again. Then I'm saying that st given st plus 1 and x1 to t is of course results from dividing the joint of st and st plus 1 given x1 to t by st plus 1 given x1 to t. So this is just definition of conditional probability. And then I'm conditioning the upper thing here on st. So st plus 1 giving st x1 to t, and pst given x1 to t. And then again st plus 1 given st is independent of x1 to t. This is the definition of the probabilistic state space model, and hence we have this conditional distribution. And then if we look at the joint distribution, we need of course the marginal. So we have pst plus 1 given x1 to t, so that's this thing here. and this conditional which we just derived. So we get to this. So when I was first confused, I was confused because I didn't show this this thing. So why does the smoothing equation work? Essentially, it works because of the conditional independence properties of the probabilistic state space model. And one can show, or what is shown here is that this joint distribution of st and st plus 1 given x1 to t takes this form. If you now integrate out st plus 1, which is done in the smoothing equation, then you get st given x1 to t. The important thing is that that you need the smooth distribution at one later time point in there. Yeah? And if you want to prove this in more depth, actually, than is done here, you would have to show that this holds. This thing. Yes, yeah, because that's not immediately clear why this should hold. So that st given st plus 1 and x1 to big T is independent of xt plus 1 to big T. So if you want to do something this afternoon, prove this based on the definition of the state space model. Now, Bayesian smoothing algorithms then use the smoothing equation, the Bayesian smoothing equation, and to do smoothing. And first, what you need are the predicted distributions, one step further than in the Kalman filter, and you need the filtered distributions. So you need st given x1 to t minus 1, or equivalently st distribution of st plus 1 given x1 to t, which we computed already in the Kalman filter, and we need the filtered distributions from the Kalman filter. So if you want to do smoothing, you first let the Kalman filter run, and then you take the parameters you get from the Kalman filter and put them into the smoother. And then you evaluate the smooth distributions using the smoothing equation. Now, the Rauchtung-Striebel smoother is the Bayesian smoothing algorithm for linear Gaussian state space model. Yeah, so again, it's like for Kalman filter and Bayesian filtering. Bayesian filtering is this general thing that's happening on the level of probabilistic state space models. It takes a specific form if you apply to linear Gaussian state space models. This specific form is called Kalman filter. Here, Bayesian smoothing is the general thing. If you apply Bayesian smoothing to linear Gaussian state space models, it's called Rauchtung-Striebel smoother, RTS smoother. And again, you can evaluate, everything is Gaussian, and you can evaluate the parameters using joint and conditional Gaussian theorems. So you get parameter update equations for your distributions, which we again will discuss in the exercise, and which are proven here. But so it's exactly the same thing. So you first think a little bit about what are the joint distributions in time, and then you apply the joint theorem and the conditional theorem, and then you do a little bit of rewriting. So in terms of the example, we already seen this. And here we have then the smooth distribution. So you can see that sometimes it's getting a little bit better. Yeah, maybe I can also show you the implementation so that you get more of a feeling of what that means in terms of, how can I? In terms of implementation. let's just I have on a common studio, but that's a bit easier. So this is the code that generated this example. So these are first the definitions. So here that's the Gaussian random walk model and its parameters. And then the random walk model is sampled. So we have the ST, which depend on ST minus 1 multiplied by this A matrix, and with a variance matrix you have the observations being sampled like this. And then for filtering, here's first the Kalman filter. The Kalman filter needs these parameters, of course, and it needs the data. And then Kalman filtering comes down to the Kalman filter comes down to implementing the Kalman filter equations. So I compute this m tilde, the sigma tilde, ut, Kalman vt, everything according to the equations. So I used here this general Python matrix multiplicator. I find Python and matrix multiplication and linear algebra not the greatest match so far. Is that a common thing? So I'm used to MATLAB, where matrix algebra is the easiest thing, but Python and NumPy, they say like they don't want to use their matrix class anymore. Then if you have arrays and you extract a column of an array, you don't get a column, and it's all a little bit annoying in Python with matrices. Or is it me?
If you take like NumPy arrays and multiplicate them.
Yeah, but I don't want to use this mulmat or something.
Yeah.
Because that's annoying. So I want code that looks like the math. And I mean, they have this matrix multiplicator now, this add sign, and they have, of course, there's also the inverse function. Yeah, I don't think it's awesome, but maybe I haven't searched deep enough for real good matrix algebra in Python. Anyway, so this is then just the implementation of the equations. So in real life, you implement these matrix equations, and in more real life, actually, there are then actually also more numerically stable versions than these basic equations that I introduced here. So there are then special forms of Kalman filter where you do some additional matrix tricks to have things be more numerically stable. And for the Rauchtung-Striebel smoother, you then start with the observations and your filtered data. And in this case, the predictions are computed again. You could also look up the predictions, but then you would have to basically go into your Kalman filter distributions and shift everything by one index, or you just compute this again. But again, it's then, oops, that's of course a typo. That's the RTS smoother iterations. Yeah. Good. So that's then Bayesian smoothing. So if you are somewhat clear about Bayesian filtering, Bayesian smoothing is not the biggest step, I would say. Good. Any questions about smoothing right now? No. Good. Then let me finish with, so we will look into the detailed math again in the exercise, so that we apply these joint and conditional Gaussian distribution theorems a bit. They are also, like when I first introduced them in lecture 3, they are really important, these joint and conditional Gaussian distribution theorems in statistics in general. Also, if you think about hierarchical linear models and how you do things there, so fixed and random effects models and so on, because it's always about you have some conditional and a marginal Gaussian, and then you look at the other marginal, so and other conditional. So it makes sense to get a little bit fluent with these big Gaussian distribution theorems to then be able to access also other theoretical frameworks. So before I stop, a couple of remarks regarding nonlinear dynamics, because this was now for the case that the transition dynamics and the emission or observation emission dynamics are linear. So you multiply the state with a matrix to get the expectation of the next state. You multiply the state with a matrix to get the expectation of the observation. Of course, you can have nonlinear state transitions and also emission observations. And three frameworks to this end here. So one is what's called extended Kalman filter and extended RTS smoother. This essentially works by approximating the nonlinear transitions and emissions using a first-order Taylor series, so that you essentially linearize these things, and then you use the Kalman filter again because you have a linear system. Another way that is, or something else that is done where I have a little bit of experience, is this unscented Kalman filter. There what you do is a little bit different. So you actually pass what is called sigma points to the nonlinear transition and emission functions, and then you have this thing that I always emphasize, that you have transformations of random variables. So you pass Gaussian distributed random variables through a nonlinearity, and then of course what you get out is not necessarily Gaussian anymore. If you transform a Gaussian by a linear transformation, you get again a Gaussian. This is what the joint Gaussian distribution theory says. But if you transform a Gaussian by a nonlinear function, you don't necessarily get a Gaussian anymore. What the unscented Kalman filter then does is to do this for a number of points, and then approximate the transform distribution by a Gaussian, by evaluating expectation and covariance. And then there's particle filtering, which goes into numerical sampling approaches, as we will discuss next week. But you have more experience because you did your bachelor thesis with nonlinear versions. I have more experience in the linear versions. Did you find it works well?
Depends. The extended function actually does not work well for many functions.
Yeah, so that's also what from me playing with extended and unscented Kalman filter. As soon as the nonlinearities get quite nonlinear, it doesn't work that great anymore. If it's a little bit nonlinear, then it still works. But then, so But of course, there are always improvements, and everything is always getting better, and there are always suggestions how to make these better. But it sounds a little bit, if you read in textbook about extended and unscented Kalman filters, if that's the solution for nonlinearities. But if you then play around with it, you find that not really. The other thing that is, of course, of interest, if you're more from a statistics perspective, is that for everything that we discussed here, we assumed we know the parameters of the state space model. So that we know the transition matrix, and we know the emission matrix, and we know the covariance matrices. And of course, you can also easily conceive the scenario where you assume that there's a probabilistic state space model, but you don't know its parameters. And then you have this double problem of inference in learning. I think that's how they used to call it in machine learning. So you need to infer the state. At the same time, you need to learn the parameters of the state space model. And then you can learn the parameters of the state space model either in a point estimate and maximum likelihood manner, or you can go full crazy and want to learn the parameter in a Bayesian manner. So to basically, then you have two kinds. Then the distinction between states and parameters is essentially that states are time varying parameters, and the parameters that you then have are non-time varying. And just to let you know where we are coming from, so this is what we looked at. So the Bayesian estimation using variation inference for these linear state space models, that's what we looked in 2014. So everything that we did today was under the assumptions that we know the parameters. If we don't know them, we have to estimate them. No, but that's, I think, it. So any remaining questions regarding Bayesian filtering and smoothing? No, not for today. Of course, like I said, one can make this notationally a little bit more complicated by letting the transition and emission probabilities vary over time. I think when you start working in data assimilation, or you come across Bayesian filtering, or you want to do, also if you want to do POMDP based AI, I would really recommend to first familiarize yourself again with Bayesian filtering and smoothing, and I really recommend this Selke book because it's really concise but also precise. Good, then I stop here.